Here is the fifth and the last part of the turbomachinery chapter. In this one, we will study the specific speed, pump selection, and talk a bit about hydraulic turbines. Specific speed, shown with NS, is a non-dimensional number. For a pump, it is obtained by combining the flow coefficient πq and the head coefficient πh in a special way such that the diameter is eliminated. As you see, we take the square root of πq and divide it by the 3/4 power of πh. What we get at the end is a non-dimensional expression that has rotational speed, flow rate, and head parameters in it. In the industry, people commonly use specific speed in a number of different dimensional forms, such as the one shown here. In this one, gravitational acceleration is missing. Speed is in RPM, flow rate is in liters per minute, and head is in meters. As you know, a pump can operate anywhere on its head curve. For all these different operating points, a different specific speed can be calculated. But we prefer to calculate a single specific speed for a pump, and we do this at the best efficiency point. Specific speed is used to classify and compare pumps and perform preliminary pump selection, which is about deciding on what type of a pump, a centrifugal, an axial, or a mixed type, is most suitable for a given application, with known required head, required flow rate, and rotational speed values. This figure shows the efficiency that can be obtained by different types of pumps working at different specific speeds. There are two horizontal axes. The lower one is the non-dimensional specific speed, and the upper one is the dimensional version. Vertical axis is the efficiency. As you see, axial pumps perform with efficiencies of about 90% at specific speeds around 4. Axial pumps are preferred in applications with large flow rate and low head, which corresponds to high specific speed. Centrifugal pumps, on the other hand, work most efficiently when the specific speed is around 0.9. They are preferred in applications with low flow rate and high head. Mixed type pumps are somewhere in between. Their maximum efficiency is obtained for specific speeds around 2.5. In preliminary pump selection, we decide on which type of a pump to use by calculating the specific speed of our application and select a centrifugal type if the value is lower than 1.5, select a mixed type if it is between 1.5 and 3.5, and go with an axial pump if the value is larger than 3.5. Memorizing these values is not important, but you need to know the definition of specific speed and also know which pump type is suitable for low, medium, and high specific speed applications. This slide is about axial pumps, which are also called propeller pumps because they look like propellers. They are preferred in drainage and irrigation applications where the flow rate demand is very high. As seen in the figure, other than the rotating blades, axial pumps can also have stator vanes, also called guide vanes. They are fixed, they do not rotate. Their job is to guide the flow to the rotating blades at the most proper angle. This figure, taken from Munson's book, compares how the head, efficiency, and power curves of centrifugal and axial pumps differ. Solid curves are for a centrifugal pump and dashed ones are for an axial one. Both pumps can provide a maximum efficiency of about 85% at a flow rate of 2.8 meter cube per second. While doing this, they both deliver a head of about 5 meters. They are quite comparable in this sense. Their efficiency curves, the red ones, look similar. However, head and power curves are quite different. As the flow rate reduces, the head and the power consumption of the axial pump increase greatly. Head curve of the axial pump, which is the green dashed curve, changes much more rapidly with the flow rate compared to the centrifugal pump. To control this high flow rate dependency better, some axial pumps have adjustable blades. Their angles can be adjusted for different flow conditions. In selecting a proper pump for an application, the most important inputs are the head and the flow rate. Then comes the speed, fluid type, available space, allowable noise level, and other minor details. We start by calculating a specific speed and first decide on the pump type. After that, we try to select the most suitable pump by examining what different manufacturers offer. Pump manufacturers usually provide catalogs of their products, and the selection process starts with charts similar to the one shown here. This one is from a Turkish company called Standard Pompa. What you see here is a head versus flow rate plot. A number of different pump families occupy different parts of this plot. One thing you need to be careful about is that this plot is provided at a certain speed. It says 2900 RPM at its bottom right corner. The manufacturer may provide similar plots for other speeds. Let's say that in our application the desired flow rate is 100 cubic meters per hour and the desired head is 30 meters. And let's say that we have a suitable electric motor to run the pump at 2900 RPM. On this chart, these values correspond to a pump family of 65-160. These numbers are usually related to the basic dimensions of the pump, such as the discharge flange diameter or the base impeller diameter. This is another pump selection chart provided by a different manufacturer. This one is for axial pumps, and that's why you see low head values but very high flow rates. Let's say that in our application we are looking for a flow rate of 5000 cubic meters per hour and a head of 4 meters. If we locate this operating point on the chart, we see that it falls on the pump family designated as 24-24 and 24. We need to examine the technical documentation of this family to learn extra details, such as the efficiency and power consumption. If we go back to the centrifugal pump selection from Standard Pompa, here are the technical details of the 65-160 family that we found to be suitable for our application. We see a lot of information here. The common horizontal axis for all plots is the flow rate. On the vertical axis, we see the head, the required NPSH, and the pump power. In this family, 3 different impeller diameters are offered as 160, 175, and 184 millimeters. There is a separate head curve for each of these shown in black color. Our operating point of 100 cubic meters per hour flow rate and 30 meters head is shown with the purple dot. Looks like that 175 millimeter option can provide it. The red curves are the efficiency contour lines. Each red curve corresponds to a different efficiency value. Our operating point is on the 65% efficiency contour. This pump family can provide a maximum efficiency of 73.5%, but it can be obtained if the largest impeller is used. This problem is from the solved examples handout. It is about selecting a pump from the catalog data provided by a pump manufacturer. What we see here is a typical crowded figure with lots of data provided by a manufacturer called Taco Pumps. First thing to notice is the figure is provided at a rotational speed of 1160 RPM, written at the top of the figure. There are 5 different impeller diameter options. Blue curves are for the pump head. We have 1 blue curve for each diameter. Green ones are the efficiency contours. Dashed red lines are the pump power contours. And the purple one at the top is the required NPSH curve. Please study the details of this example and learn how to read these figures. The rest of this chapter provides some preliminary information about hydraulic turbines. Here we see the typical head and flow rate ranges of different hydraulic turbine types. The most commonly used ones are Francis and Kaplan types, shown with red and blue colors respectively. Generally speaking, Francis turbines can work at higher head values, and Kaplan turbines can work at lower heads, but at a wider range of flow rate. Among the three impulse-type turbines listed here, the Pelton wheel is more popular. It is shown with purple color on the top left corner of the plot. Pelton wheels are low flow rate and high head devices. It's worth to note that although the maximum power value seen on this figure is 10 megawatts, today's modern hydraulic turbines can provide much more than this. Therefore, not the numbers, but the trends are more important in studying this figure. As you know, the fundamental characteristic of a pump is its head versus flow rate curve given at a certain rotational speed. The fundamental characteristic of a hydraulic turbine, on the other hand, is the power produced versus the rotational speed given at a certain head. Unlike a pump, the head of a hydraulic turbine is more or less a constant value, which depends on the water resources available at the site of the power plant. Turbine-specific speed is a spatial combination of the power coefficient and the head coefficient such that the diameter is eliminated. Similar to pumps, it is used for quickly deciding on what type of a turbine is the most suitable for the job. This figure shows the typical efficiencies of different types of hydraulic turbines at different specific speeds. Impulse-type turbines, such as Pelton wheels, are suitable for low specific speed applications. This corresponds to low power and high head. Kaplan-type turbines work efficiently at the other extreme. They are suitable for high specific speed applications, which typically correspond to low heads. Francis turbine is the most commonly used hydraulic turbine, and it works most efficiently at specific speed of about 1. Here is what a Pelton wheel looks like. Several buckets are attached to a rotating wheel. Buckets have special designs. They split the incoming water jet into two and turn it backwards. This transfers the momentum of the incoming jet to the rotating wheel. As you see, the buckets have a cutout part. The reason for this can be seen in this figure, where we look at the turbine from the top. The water jet coming from the left is allowed to pass through the cutout opening of one of the buckets to hit the one behind. This allows a more effective momentum transfer. Do you remember the theoretical head analysis we performed earlier for a centrifugal pump? A similar idealized analysis can also be performed for a Pelton wheel, which is actually simpler. Although not given here, you can find its details in your textbook. The general design and the most important components of a Francis turbine are shown on the left. The fluid first passes through guide vanes. These vanes are not attached to the shaft and they do not rotate, but their angles can be adjusted so that the fluid is directed to the rotor blades at the most desired angle as the conditions of the power plant and the demand for electricity change. Then the water passes through the rotor blades, also called the runner of the turbine, and the water leaves the turbine through a draft tube, which is actually a diffuser, slowing down the exiting water and increasing its pressure. Here is another, more detailed schematic of a Francis turbine. Rotating runner blades are the most inner ones, shown in brown color. Before the runner, there are the wicket gates, which are nothing but the adjustable guide vanes we saw in the previous figure. And before the wicket gates, there are the non-adjustable stay vanes that we have not seen in the previous figure. Similar to a pump, the outer casing is called the volute. If we go back to our slide, the general design of a Kaplan turbine is shown on the right. Fluid again first passes through the adjustable guide vanes. Then it turns 90 degrees before passing through the runner. At the inlet of the runner, which looks like a propeller, fluid motion is mostly axial, that is parallel to the shaft. Remember that Kaplan turbine is an axial flow machine, whereas the Francis turbine is of mixed type. Here is what Francis and Kaplan turbine runners look like. The Francis runner shown here has more than 10 blades, and the Kaplan turbine has 5. As you see, the blade designs are totally different. Idealized theoretical calculations for the runner of a Francis turbine are very similar to that of a centrifugal pump, as you can see in the solved examples handout. In those simplified calculations, we can think of it as a backwards running radial pump. Theoretical calculations for a Kaplan turbine are similar to those of an axial pump or a fan, which are also given in the solved examples handout. But this semester you are not responsible for the theoretical analysis of axial flow machines. This exercise is about the use of specific speed and similarity concepts for hydraulic turbines. It mentions about a turbine called turbine A, which has a satisfying performance. Its diameter, speed, flow rate, head, and power production capacity are all given. We want to scale up this turbine for a larger power plant which has a higher head. The new diameter and a few other related quantities for the new turbine are asked. Here is how we can solve this problem. The two turbines will be geometrically similar, and they are expected to have the same specific speed, which can be calculated using the properties of the first turbine at its maximum efficiency point. Using the same specific speed and the new head value, the power consumption of the second turbine can be calculated at its best efficiency point. Then the maximum efficiency of the first turbine can be calculated. Due to their similarity, the maximum efficiency of the second turbine can be only as much as that of the first one. And by using the previously calculated power production and efficiency values, the unknown flow rate of the second turbine can be determined. In the first exercise of this slide, we are asked to calculate specific speeds of different hydraulic turbines. The data provided here is actual data because these are real existing turbines. This is what the Smith Mountain Dam mentioned in part B of the exercise looks like. Actually, this is a pump storage hydroelectricity facility. During the time of the day when the electricity demand is low, the turbines work backwards, functioning as pumps to pump water from the lower reservoir to the upper reservoir. And when the electricity demand peaks, water flows from the upper reservoir to the lower one, and this time turbines generate electricity. Let's watch a short video about this concept.
Australia has a big challenge ahead with its energy supply. Almost 3/4 of Australia's energy comes from coal, which will decrease in coming decades as coal stations close down. We'll need huge amounts of new energy generation to replace it, and renewables such as wind and solar are the cleanest and cheapest option. That's where Tasmania can help. We're looking at the potential to double Tasmania's electricity generating capacity by changing the way we use our existing hydropower system and by adding pumped hydro storage to help fill the gap when the wind isn't blowing or the sun isn't shining. Normal hydropower is created by storing water on high ground and running it downhill to spin a turbine at the bottom. Once the water's past one or more turbines, it flows on out to sea. Pumped hydro captures and stores water in two places with a steep drop in between. Water can be pumped uphill to reuse for power generation again and again. Of course, that pumping consumes electricity in itself. That's where wind and solar power come in. Pumped hydro, wind and solar complement each other beautifully, providing a stable, reliable, clean energy system. When the wind blows and the sun shines, but people aren't using much power, excess wind and solar power is available to pump water back up into storage. At other times, when the wind and sunlight aren't generating enough power to meet demand, the pumped hydropower system swings into action and makes up the shortfall. The whole system works together like a giant renewable battery, providing the storage, reliability and flexibility that wind and solar can't offer on their own. Tasmania has lots of steep hills that were perfect for building hydro over the past century and are ideal for developing pumped hydro today.
As you watched, in the concept of pumped hydro, Hydraulic turbines are combined with other renewable resources to create a two-way system. If we go back to the exercise, you need to calculate the required specific speeds of each of these turbines and locate them on the specific speed figure given in slide 68 to see whether they are working efficiently or not. The second exercise of this slide is asking for the meaning of a number of hydroelectricity-related terms. We actually studied many of them, such as the runner blade, wicket gate, stay vane, and draft tube. The new ones are the crown, penstock, and tail water. This figure shows a schematic of a Francis turbine. Flow first passes through the stay vanes, then the wicket gates, and then the runner blades. The runner blades rotate between the crown at the top and the band at the bottom. And here we see the schematic of a hydroelectric power plant. Water is stored on the left side of the dam. Penstock is the passage that goes through the dam joining the lake and the turbine. By opening the head gate, we allow water to go through the penstock. Here is the turbine generator assembly connected with a shaft. We have the draft tube at the exit of the turbine, and the water exiting the draft tube is known as the tail water, shown here as tail race. If we insert a pitot tube at the end of the penstock, which is the entrance of the turbine, and another one into the tail water, the difference of the water levels inside these tubes will give us the net head of the turbine. Therefore, when we say a turbine with a high head, we mean that this elevation difference is high. One obvious way to increase the head is to build a lake with high water level, which of course is not always possible because it depends on the geography of the site of the power plant. This is the end of our turbomachinery chapter. We haven't talked much about certain machine types such as compressors, gas turbines, or wind turbines. If you are interested in them, you can read a bit about them in your textbook. Also, if you like this chapter, you can consider taking the Fluids Machinery course as a technical elective next year.